Okay, now that you made it through that last video, we're going to start off infinite limits. Now, while this sounds much worse than common factors or canceling like we did in the last video, infinite limits are really conceptual and are actually easy if you just think about what's going on. So I'm going to start it off with some notation. Um, as you know, infinity is represented by this symbol. It's kind of like a sideways 8. Um, just in case you didn't know that going into this. I'm not going to judge anyone if you didn't know it. Okay, so we'll say limit as x goes to infinity of 1 over x. Now, I'm just going to start off with this one because this one is a really central limit to understand, a really important one to get if you want to do well in the AP or just understand calculus. So what we have here is when we plug in a certain value for a limit, it's easy, especially here. If we picked any x we wanted to, we could just plug it in here and that's the limit. If x were 5, plug it in, it's 1 over 5. But when we're dealing with infinity, we have to think about what the graph looks like. This is the best way to understand it, is to visualize it. Now the graph of 1 over x looks like this. Now it won't be completely to scale, but you get the point. This is what the graph looks like. So we're saying what happens as x goes to infinity? What happens as we go as far in this direction as possible? Now you'll notice this line comes here and keeps getting closer and closer and closer and closer. So what we ask ourselves is, what is the limit? What does this actually end up going to as it goes to infinity? Now, if you can tell by the graph, the answer to this is 0. Because what happens is the numerator never changes, and the denominator keeps getting bigger and bigger and bigger, and the number keeps getting smaller and smaller. And if the number becomes infinitely small, we can say it's basically 0. Now, if you understand this, we can go on to the next one, which is a lot easier. The limit as x goes to infinity of k, which is a constant, meaning any number, any constant value that doesn't change, there's no x involved here, equals k. Now what this means is if we have a graph here, and we pick a value for k, say 5, if we pick a value for k, it's 5, this graph just goes infinitely far in this direction, always the same at 5. So our limit is just k. And the same is true if you go in the opposite direction, this way. Now, what we say when we're talking about this direction is the limit as x goes to negative infinity. Really easy. Just going as negative as possible. And if we look here, if we wanted to look at the limit as x goes to negative infinity in this example, it's the same thing. It's just we're approaching from the negative side, but this is going to go on and on and on and on and on until it touches 0. It never really touches 0, but at infinitely far of a distance it will touch 0. Or we can say that it basically touches 0. Okay, now that we've got these out of the way, I'd like to go over 3 more types, 3 general types, and remember, if you understand these, you'll be fine. Just remember to really think about what's going on in each of these examples. Oh, and yeah, this associates with that. Just add that in. Okay, anyways, so let's take a look at when the numerator and denominator are in the same degree in an infinite limit. What this means is x goes to infinity, and let's say we have 9x squared minus 2x plus 1 over, let's say, 5x squared plus 30x minus 10. Okay, now these look like some pretty complicated numbers, and you'll be thinking, oh, this is that thing where we have to factor, but no, that's not the case in infinite limits. All you have to do with infinite limits is remember that what we're dealing with is what happens at infinity, what happens at the outermost stretch of the graph, as you go as far right as possible. And if you think about it, when you start moving really far in the positive direction, this term and this term are squared, so this 5 squared goes to 10 squared, goes to 50 squared, and it keeps growing exponentially, or at least keeps growing as squared. So at the same time, this negative 2x and this plus 30x are only increasing by x each time, whereas this is increasing by x squared. So as we go to infinity, we can essentially say that we only have to look at these. Now, this is kind of a difficult concept to grasp because you'd think, well, what about all the rest of this? But in the scheme of things, negative 2 times something is completely washed out by these x squared terms because they grow so much faster. If you think about it, 9 times 10,000 squared is 10,000 squared is way bigger than 10,000. So imagine if you were going to billion, trillion, up to infinity. So, and obviously this plus 1 and minus 10 term are insignificant. So all we have to do is think about what is significant in each of these. Now, once we do this, we can just pretend it looks like that. 9x squared over 5x squared cancels to 9 over 5. And that would be our answer. Now, let's try one where we have a smaller degree in the numerator. Okay. Now for this one, we're going to say the limit as x goes to infinity again. Of anything. Let's say 4x minus 1 over 2x squared plus 3. That's an easy example. Now, this one, we have the bottom growing faster, and you might think that this is going to end up at 0. In fact, I'm not exactly sure. I think it might always end up at 0, but the way I learned how to do this is to just divide everything by the largest term. So what that means is take your largest term, largest x component, which is x squared, and divide everything in this by x squared. So divide by x squared on the top, and divide by x squared on the bottom. Now what we get is, okay, 4x divided by x squared is going to be 4 over x, minus 1 over x squared, and that's all over 2 plus 3 over x squared. Whoops, okay, sorry. 3 divided by x squared. Alright, now this looks even worse, and this looks pretty confusing, but we have to go back to lesson 2, which was talking about limit rules. The same limit rules apply for infinite limits, and what that means is you can break this down, so you don't have to take the limit of this entire thing. You can do it piece by piece and just add them up. So let's do that. The limit of this, of 4 over x, as x goes to infinity, we look back here. It doesn't matter if there's a 4 on the top or not, because as x keeps growing, where the numerator stays the same, it keeps shrinking, shrinking, so this goes to 0. And then we subtract. Same thing here. X keeps getting bigger as x goes to infinity, whereas this stays the same. The denominator keeps growing, so this goes to 0. On the bottom, we have 2, that's a static number. This is going to be the way it is. And then add, same thing on the top, this is going to be 0. 2 plus 0. Now this cancels to 0 over 2, or not cancels, but that goes to 0. And if you think about what we had here, that makes sense, because in this original limit, we took, as x goes to infinity, this term here in the bottom keeps growing faster and faster, and this one just can't keep up with it, especially when it gets to the really high numbers. So because the denominator is growing faster, it's going to go to 0. But if you want to be sure, this is how you really show that what you're doing is correct. It's by dividing by the largest term. Alright, now I'm going to go back and make some space. I'll erase some of this stuff that we already did. Okay. Now let's go back. And our last one is going to be if we have a larger factor on the top. Okay, so I'll go ahead and make an example. Okay, so let's think. If the numerator has a larger degree, let's go with the cubed term this time. So 5x cubed minus 2x squared plus 3x minus 1 over 4x squared plus 8x plus 7. Okay, that's good. Alright, and I didn't put this in yet. This is really important. Can't leave that out. Limit as x goes to infinity. Okay, so what we do now is the same thing we did over here. But instead of dividing by the largest, we divide by the largest on the denominator. So what we get now is limit as x goes to infinity of, okay, so if we're dividing by x squared again, then we get 5x minus 2 plus 3 over x minus 1 over x squared then on the bottom we get 4 plus 8 over x okay, hopefully that looks a little better, plus 8 over x plus 7 over x squared. Now again, we have something kind of crazy here, but all we do is look what happens when we go to infinity for each term and break it down. So we get, as x goes to infinity, for 5 times x, we just get infinity, because as x goes to infinity, boom, x goes to infinity, minus 2, then if x is in the denominator, plus 0, minus 0, and on the bottom we get 4 plus 0 plus 0. Now, if you look at this, you can look at these first terms and say that, okay, the top's going to dominate. The bottom never changes, and the top keeps growing higher and higher. So it's clearly just going to go to infinity. But if you're not comfortable just saying that, you can go ahead and plug everything in, and then, you know, it doesn't matter, infinity minus 2 over 4, that's just silly. Our answer is going to be infinity. But if we said as limit of x as it goes to negative infinity, we get something slightly different. This term at the top is going to get more and more negative, infinitely negative, as this denominator stays the same. So what we're going to get as an answer is going to be negative infinity. So you have to watch out whether you're going to infinity or negative infinity. Now, I'm almost out of time, so that should wrap things up for your introduction to infinite limits. This seems kind of crazy, so make sure you review this and do some practice questions if your teacher assigned them. And thanks for watching. I'll be back with some more infinite limits